All right, we're back with some more homework help. But this one's not a homework problem. These are the warm-up questions that we looked at in class as we were getting ready for the solution stoichiometry quiz. So we're going to go through these two. Again, I'm just going to talk through the solutions that I already have written and just kind of talk about my thought process and like when I was writing the questions, what are my intention, if I was solving the question, like what am I looking for, all that good stuff. Okay. So we're told that we prepare a solution by mixing 0.1 liters of 0.12 molar sodium chloride with 0.23 liters of 0.18 molar magnesium chloride. And we want to know what volume of silver nitrate that we need to add to this new solution that we've mixed together to precipitate all of the chloride, right? We want to precipitate all the chloride ions in the form of AgCl. All right, so if we're reading that question, like what information are we getting? So first, because we're precipitating all the chloride, that is my indication that the Cl minus is limiting. Right? If all of it precipitates, that's our limiting. So let's first start with figuring out how many moles of Cl minus we have. So I'm doing concentration times volume, actually volume times concentration of the NaCl. It's a 1-to-1, so 0.012 moles of Cl minus. Volume times concentration of the magnesium chloride. Now this is MgCl2. I did see a lot of people make the mistake here of like not having like this written correctly, MgCl2. Remember that we gotta balance charges, right? We gotta like do the thing. We don't want to skip those pieces. Those pieces are like really important. So we have twice as many Cl's as we do MgCl's, so it's 0.0828 there. Now for this precipitation reaction, we're precipitating AgCl. I don't care where the chloride comes from, right? It doesn't matter if it came from the sodium chloride or it came from the magnesium chloride. In the reaction, it's going to get used the same way. So I'm figuring out our total moles of chloride, right? I'm just adding these two things together. Because it doesn't matter, like where it was sourced from. When it goes into the mixture, the Cl gets released from the sodium and the magnesium, right? It ionizes, and it's floating around and it's ready to react. So we just need to figure out how much in total we have there that is ready for the reaction. And the reaction is given over here. I use the net ionic for this problem because since our chloride's coming from two different places, it's just easier to make this like Cl minus. And specifically, this is our total Cl minus, right? Like it's all the chloride that's in the solution. All right, and then we just do some stoichiometry. It's all a 1-to-1, so it's a little not exciting, but here's our total moles of chloride, 0.0948. We're working backwards. We need to figure out how much silver we need to add. So we go back to silver, or we go over to silver, 1 Ag, 1 Cl minus, and then to silver nitrate. Again, it's a 1-to-1. So we figure out that we need 0.0948 moles of silver nitrate, AgNO3. We're told the concentration of AgNO3 in the problem, 0.2. So I just am plugging in my two values, 0.2 molar, 0.0948 moles, and I'm solving for liters. I also saw some people get tripped up on that. Remember that we have our triangle. Let's write it up here. Triangle. Looks like that. And whatever you're solving for, you're going to cover it up. So let's cover up our liters. And so that shows me that in order to solve for liters, I need to do moles over molarity, right? So if it's easier to do this than rearrange your equation down here, please do that. I did see like a lot of people solve this like the wrong way. But that's what we're doing. We're solving for liters, so we're going to cover that up. Moles of AgNO3 over molarity of AgNO3 gives us 0.474 liters or 474 milliliters. Okay. Important part about this problem is this. This is kind of like the crux here, right? Combining your chloride. The idea that it doesn't matter where the chloride came from, right? Doesn't matter if it came from the NaCl or the MgCl2. It's going to react all the same. So we just need to put it all together. All right. So now let's look at part B. We're going to slide over to the next slide and do that. All right, part B. So I've got all my pieces of my solution screenshotted here. It's a little messy, but I think we're going to be able to make it work. So we want to calculate the concentration of all the ions in solution after the reaction, right? Classic part B question after we do a precipitation reaction. So kind of the tricky thing about this one is usually there are 4 ions in solution. This one we have 5, right? So we've got the Na, we got the Mg, we got the Cl, we got the Ag, we got the NO3. So these are all the possibilities, right? This is just thinking about like what was present before any reaction happened. Again, our big idea is that we can always find out how many moles remain by doing the moles that we had initially minus the moles precipitated, right? That always works. But conceptually, we can take some shortcuts if we understand the phrasing of the problem. And so that's what I'm here to do. I'm here to talk about some of the phrasing that we've got here. All right, so I pointed out that in this question, it's told that we're going to precipitate all of the chloride, right? That means it's a complete reaction. All the chloride precipitates. So that means that the concentration of Cl minus is 0 in solution. All of it precipitated. It all came out as a solid. So there's no aqueous chloride left in solution. Now, the way the question's phrased, we can also infer that all of the silver also precipitated, because in part A, we were just calculating like the minimum amount needed to precipitate all the chloride. So assuming that we have 100% like efficient reaction, which by the way in reality is usually not the case, but we're not asked to like, kind of bridge that gap in the problem, right? We just want to, under ideal circumstances, I guess is the best way to think about it. All of the silver would also precipitate, right? This was a perfect mixture here, right? Perfectly mixed so that all the chloride and all the silver come out of solution. Okay, so its concentration was also 0, right? Now we could have gone through and you can like do the math, right? Figure out how much precipitate was made, right? Do your whole thing, and you would get, your moles initial minus your moles precipitated are going to be the same. So you would do the subtraction and get 0. So you could take the long way there, but that's our conceptual shortcut. All right, let's move on to our spectators. Na and Mg are spectators in this reaction. Sodium, always a spectator. Always a spectator. There is never a time when sodium is going to precipitate. Magnesium, sometimes a spectator, sometimes not a spectator. In this one, not a spectator. In this one is a spectator because it's mixed with the chloride. If it was something like a hydroxide, something like that, we might see magnesium come out of solution. In this case, it didn't. It's a spectator. So they don't precipitate. So their moles didn't change. Their moles initial and their moles remaining are the same. In other words, their moles precipitated is 0, right? So moles remaining equals moles initial. So I've already got those numbers in my part A calculations. This is volume times concentration for the sodium chloride, volume times concentration for the magnesium chloride. You can get moles of sodium, moles of magnesium. So those are the same, right? 0.012 and 0.0414. And then NO3, also a spectator, okay? Again, NO3, always a spectator. Never an instance when NO3 is not a spectator. NO3, always a spectator. Now this one is a little more roundabout way to get to this number of moles. So in our calculation, we figured out that we have 0.0948 moles of AgNO3. That was kind of like the result of part A. And so what I'm looking at here is that there's 1 NO3 per 1 AgNO3, right? It's a 1-to-1. So you get 0.0948 moles of nitrate as well, which is what I have here, right? So again, the idea here is that we had all these numbers like already in our calculations for part A. You just kind of have to go up there and like figure out like which one you need, right? You could also like redo the math, but we work smart, not hard around here. All right, so we got our moles of sodium, our moles of magnesium, our moles of nitrate, and of course our moles of chloride and silver. And now we're ready to do concentrations. So we're just doing moles over volume. Total volume here is 804 liters. Gosh, no. 804 milliliters or 0.804 liters. This is also like a little bit of a tricky part of this problem. you had 0.23 liters, 0.1 liter, and then you also added the 700 or the 474 milliliters from part A. So you're adding all three of those things together for a total of 804 milliliters. Okay, 0 over 0.804 is 0. 0.012 over 0.804 is 0.0149. Probably 2 sig figs is better there, but you know, it's not a big deal. 0.0414 over 0.804, 0.0515, and then the nitrate 0.0948 over 0.804 is 0.118 molar. Okay, so here are our concentrations, right? So again, key part to this problem is understanding, you know, what we meant by limiting reactant, like all that stuff. You had 5 ions here, not 4 like we normally have in these problems. And then we're getting total volume here. So it's not only from what was in the problem, but also from what was in part A. And this idea of like using an answer that you got in part A to like continue to do the problem in part B, that's another like really common thing in AT chemistry. A lot of our problems, like you're taking part A and you're bringing it into part B, and then part B goes to part C, and part C goes to part D. I write problems like that because it helps like break them apart into like a little bit like smaller chunks that are easier to grade and easier for you to read. The downside of that is if you don't get part A, sometimes it's hard to continue with the problem, but we'll cross that bridge when we get there. All right, so there's is warm-up problem number 1. We're going to go forward. We're going to do warm-up problem number 2. I did rewrite that one a little bit, so we'll go look at the new version and talk about it. All right, so question number 2. So as I mentioned, I did a little rewrite on this from what we saw in class to make the answer a little less ambiguous. And the nice thing about this question is there's no math that we're doing here. This is sort of just like a puzzle, kind of akin to the Which 9 Solutions lab. Okay, so we're told a solution contains one of the following ions. So the silver cation, the calcium cation, or the sodium cation. And we're going to take the solution, we're going to add some other known solutions to it and see if a precipitate forms. So we first add sodium chloride, no precipitate. Then we're going to add sodium sulfate, and we get a precipitate. We're going to remove the precipitate that formed, and we're going to add sodium carbonate, and then we get another precipitate, right, or more precipitate forms. And so we want to decide, or we want to figure out, is it silver, calcium, or sodium that's in the solution? So when we worked through this, I saw some folks doing like a reaction matrix, you know, kind of like the Which 9 Solutions lab. And I think that's great. I love that idea. I kind of just think about it in steps, right? So step 1, we're adding the sodium chloride. Step 2, we're adding the sodium sulfate. And step 3, we're adding the sodium carbonate. And then asking myself, like, what precipitate would I expect to form out of each of those steps? So let's take step 1 first. Of course we would, right? It's the first step. So if I add sodium chloride, does calcium chloride precipitate? No. And I could go to my blue sheet and I could see that calcium chloride is soluble. Would silver chloride precipitate? Yes. So if silver is in this solution, I would expect a precipitate upon the addition of NaCl. So since this Cl- doesn't produce a precipitate, Ag must not be in this solution. Otherwise, we would have seen a precipitate in step 1. Okay, so we've already kind of eliminated one of these. We don't think silver is here, right? So let's narrow it down. Is it calcium or is it sodium? When we add the sodium sulfate, we get a precipitate. So again, I ask, does sulfate precipitate with calcium? It does. On my blue sheet, it says that it does. So that's probably the precipitate that we made. Does sodium precipitate with sulfate? No. All sodium salts are soluble. No sodium salts precipitate. So seeing a precipitate in step 2 is kind of leaning me toward Ca2+ as my answer, right? That there's calcium in this solution. All right, let's go to step 3. We're adding the carbonate. When I add the carbonate, I produce another precipitate. Is that going to precipitate with calcium? Yes. Calcium carbonate is a precipitate. It is insoluble. Does sodium precipitate with carbonate? No. So again, the idea that I'm seeing a precipitate there is drawing me toward the idea that calcium is in this solution. Okay, so that's my answer. I think it's Ca2+. If there were no precipitates formed in step 1, 2, or 3, I think it would be sodium, because sodium doesn't precipitate with anything. If we would have made a precipitate in the first step, the Cl-, then we could assume that there's also silver here. But since we didn't get a precipitate in that first step, I don't think silver's in the solution. Okay, so my two precipitates are calcium sulfate, calcium carbonate. There's my two net ionics for those precipitation reactions, and I think that's our answer.